Thank you very much. So today I'm going to talk about the exploit development process for an IE11 exploit we developed beginning of this year. And since we were targeting IE11 on the latest version of Windows 10, we had to bypass quite a few exploit mitigations. And so in the end, we decided to submit all the vulnerability information and all the techniques we were using to Microsoft as part of their mitigation bypass bounty program. And I'm quite happy to say that we got awarded the full $100,000 US for our submission. So today I'm finally able to publicly disclose all the techniques and vulnerabilities we used, and I will show you all of that basically. So I will start with some motivation, basically explaining why we started developing the exploit in the first place. And after doing that, I will go through each technique and vulnerability. So starting with a typed array neutering vulnerability, which is the bug we exploited to get the initial code execution. I'll talk about IE's custom heap and how we used that in order to turn the bug into a read-write primitive. I'll talk about God mode, which is a known technique, or previously known technique, which can be used to get code execution without using shellcode. And I will talk about how we actually managed to re-enable that or reuse that in the latest version of Internet Explorer. I'll talk about how we managed to escape the enhanced protected mode sandbox. And finally, I'll talk about the generic technique which allowed us to make our exploit work under Emmet. So a few words about myself. My name is Moritz Jodeit. I'm head of research at Bluefrost Security, which is a small research-based company in Germany. And my main focus is on application security. So I'm mostly interested in stuff like reverse engineering, bug hunting, exploitations, and I like to poke with mitigations. So yeah, why did we actually start doing the exploit? So the initial idea was that we wanted to participate in Pwn to Own this year. So after thinking about a bit which target we could choose, we decided to go after IE11. Mainly because, first of all, we had some prior experience with it, and second, just based on the previous year's rules and prize money, we thought that that the expected difficulty versus the expected prize money was just right for this target. So the goal was to exploit IE11, the 64-bit version. Enhanced protected mode had to be enabled manually because that was a requirement in the last year's contests. It had to be run on the latest version of Windows 10, and also it had to bypass the latest version of Emmet as well. So basically we started the main work beginning of this year, and roughly a month later we already got an exploit. We got a bit lucky because we found a really nice vulnerability, and of course we didn't have an EPM escape ready, and we didn't have the Emmet bypass ready, but in general we got code execution and everything looked good so far, and we thought we would make it for Pwn to Own. Then just a few days later, Pwn to Own published the rules. And it turned out IE11 is for the first time no longer part of the contest. So we were really frustrated because we spent quite some time and effort in getting to this point. So we were thinking, okay, what can we do now? And in the end, we decided to submit all the vulnerability details and the whole exploit and all the techniques to Microsoft directly, as part of their mitigation bypass bounty program. And it turns out that was exactly the right decision because, as I said before, they awarded us with the 100K payout. So in the remaining presentation, I'm now going through all the vulnerabilities and techniques. So we'll start with the typed array neutering vulnerability. In order to understand that, you have to know about two basic JavaScript concepts. First one is web workers, and the second one are typed arrays. So web workers are basically a concept of having concurrent threads of JavaScript code running in the browser. There's a way to communicate between workers. So you use message passing. So basically what you do is you call the post message function, you pass it the message you want to send, and there's an optional argument called the transfer list. And the transfer list can actually be used to transfer the ownership of an object to another worker. And what happens in that case is, if you do that, an object becomes unusable, also called neutered in the current context, and it appears in the receiving context. So it's a way of transferring objects between workers, basically. And the second concept, typed arrays, you probably all know about them because they are really popular in recent browser exploits. Just because they give you a really powerful primitive. So once you are able to corrupt a typed array, you basically get the ability to read and write arbitrary memory, which is really powerful. So the implementation is basically split between views and buffers. So view can be seen as something like a typecast, so it just defines the way how data is accessed. While the buffer is actually the part which stores the actual data. Buffers are implemented in the array buffer object, and this object can't be accessed directly. So you always have to use a view or one of these subclasses like uint8 array or uint32 array. However, you can get a reference to the underlying array buffer of a typed array by using the buffer property. So before we actually started to look for bugs, in general it's always good to have a look what other people did in the past, because in many times it's just a quick way of finding new bugs. And it's also interesting to see where people might have looked for bugs already. So let's take a look at Pwn2Own 2014. There were in total 3 Firefox exploits. And interestingly, 2 of them were really in related areas. So the first one, exploited by GeoHot, was a bug which, so the bug description says out of bounds write through typed array object after neutering. And the second bug, exploited by Juri Edler, was also related to neutered array buffers. So it looks like this whole concept of neutered array buffers, or the whole neutering concept, seems to be error prone and hard to implement. We were looking into these techniques and these technologies and see if maybe IE11 had some issues as well. And it turns out, yes, they do. So this is our small proof of concept. It's pretty simple, it's pretty straightforward. So what we do first is we create an empty worker. So it doesn't contain any code, it just creates an empty worker. And then we create a typed array on line 5 here. And what we do now is we call the post message in order to transfer the ownership of the underlying array buffer of the typed array to this worker. And by doing that, what happens is the array buffer will actually be, or it will disappear in the current context, so it will be neutered, and effectively that means it will be freed. So after a few milliseconds, the underlying array buffer of the typed array will be freed. Since they didn't adjust or they didn't account for this fact, they didn't invalidate the array buffer reference in the typed array. So effectively, after this happened, we can just use the array and we can use it to access the freed array buffer. And this is nice because we can use the index of the array to specify the exact offset where we want to access the freed memory, basically. And we can read from it, we can write to it, so we have good control over the freed memory. So if you enable page heap, for example, you get this. So as you can see here, we are writing a single byte to the freed memory, and in this case, we control the offset, which can be found in the ESI register. So as I said, this is a pretty powerful bug because compared to other use of the free bugs where you need to find a certain target object of exactly a specific size, in this case we control the size of the freed memory. So if you know there's a nice target object which we want to corrupt of a specific size S, we could just create a typed array and thus create the underlying array buffer of exactly this size S. trigger the bug, and then we just have to force the creation of our target object, which will eventually be placed in this free chunk of memory. So it's pretty powerful. So the question is, okay, which object do we target? To answer that question, we have to first see where the array buffer is actually allocated. So if you take a look at the JS JavaScript array buffer create function, you will see that they're using the malloc function to allocate the memory. And that means the memory is allocated on the CRT or on the process heap. This actually reduces the number of potentially useful objects a bit, because all the nice stuff which you could corrupt, like typed arrays or other arrays or strings, they are allocated on IE's custom heap instead. So the question is, which object could we target in the end? It turns out there's one interesting object, which is called the large heap block object, which builds the foundation around IE's custom heap. And it turns out you can trigger the creation of these objects on the CRT heap by creating large JavaScript objects. So you can just create a large array object of integers, for example, which will eventually create these large heap block objects. And there's one thing to note here, that if you create a large array of integers, a large heap block object of a certain size will be created. However, if you create an array of object references, for example, the large heap block object which will be created has a different size. So by changing the elements you're storing in the array, you can change or you can control the size of the large heap block object which is created. Just keep that in mind, because we are making use of that in the exploit. So if you are executing the JavaScript code on the previous slide, you will see that you get lots of these allocations of B8 size bytes. And if you take a look at the memory of these allocations, you will see that these are really the large heap block objects we are looking for. So let's take a look at the content of these objects. There are some interesting fields in them. So at offset 8, there is a pointer to the IE custom heap. So this is nice, because this way we can get a reference to the custom heap, which becomes useful afterwards. At offset 58 and 60, there is a forward and a backward pointer, which usually is set to null, and I will talk about that in a bit, why this is interesting. And finally, at offset 70, there is a pointer to the large heap block itself. So this is nice, because by leaking that pointer, you immediately find the address of the current large heap block object you're operating on. So how do we actually use this for corruption? So I said there is this forward and this backward pointer. And it turns out during garbage collection, the code is actually iterating over all the large heap block objects, and it's calling the operator method on all of them. And this operator method, what it does is it performs a doubly linked unlink operation on these two pointers if they are set. And now you would expect, okay, on the latest version of Windows, these unlink operations, they are probably protected like in every modern heap allocator implementation. However, it turns out they are not. So it's really a simple doubly linked unlink operation, and you can really exploit them like you did in the past when corrupting heap metadata, for example. So you easily get by overwriting the forward and the backward pointers, you easily get a write 4, or in this case, a write 8 primitive. You have this constraint that the backward pointer actually has to be a valid address, because it's dereferenced to store the forward pointer. However, in the end, it gives us the ability to write a pointer to an arbitrary address in memory. So that's nice. However, we want something more. So we want the ability to read arbitrary addresses, we want to write arbitrary addresses, and we also want to leak arbitrary JavaScript objects. So as I said before, typed arrays are a nice way of getting this powerful primitive. However, typed arrays are allocated on IE's custom heap. And with the bug we have, we can only access objects on the normal CRT heap. So how do we find the address of a typed array? So the strategy is as follows. So first we create two groups of typed arrays. We basically create these typed arrays, which will effectively create the corresponding array buffers on the CRT heap. And we are creating one group of a specific size and another group of another size. And then we'll trigger the bug. So we will have typed arrays pointing to freed array buffers. And then we will start to alternate between allocating JavaScript arrays of integers and JavaScript arrays of typed array references, basically. And these will eventually, the created large heap block objects will eventually fill the freed heap chunks. And in order to understand it a little bit better, here's a small demonstration. So on the left side, you can see the CRT heap. On the right side, we have the custom heap. So we start by creating the first group of typed arrays. And in this case, we create typed arrays of size B8, which will effectively create array buffers of the same size on the CRT heap. Then we create the second group. So we create another group of typed arrays, but this time we create them with a size of A0. And again, array buffers will be created on the CRT heap. So now we start to do the allocations of these array objects. First of all, we trigger the bug, of course. So now we have typed arrays pointing to freed memory. And now we start to do the alternating between creating arrays of integers and arrays of typed arrays. So first we create an integer array, a large integer array. And as I said before, this will trigger the creation of a large heap block object. And in this case, since we are storing integers, it will create a large heap block object of exactly B8 size. So eventually it will replace one of the previously freed array buffer objects. And then we will continue and we will create an array of typed array references. Again, this is a large array, so it will create a large heap block object of the size A0 in this case, because we are not storing integers, but references. And now you can see why we created the second group of typed arrays, because now the large heap block object has exactly A0 bytes. So we continue that process, so we continue to create a new integer array, which will again create another heap block object. So in the end, we are exactly looking for this memory layout, which you can see on the bottom right. So what we really want to have is we want an integer array at the beginning. It needs to be followed by an array of typed arrays, and one of the reference typed arrays must be followed, and finally at the end we need another integer array. The good thing is, of course, there's randomization going on, so you can't be really sure that you trigger exactly this heap layout. However, as you will see in a bit, it's quite easy to see if you actually manage to create exactly this layout. And if you didn't manage to create it, we can just retry. So it's pretty easy to, in a loop, try to create this layout. And once we got that, we continue with our exploit. So the first step in the exploit is to actually corrupt the first integer array, this one here. So how do we do that? So we have the typed array here, which allows us to access, to read and write the large heap block object. So as I said before, there's this data pointer pointing to the CRT heap, which in this case points to the integer array. So we just leak that pointer, so we find out the address of the integer array. And then what we do is we use the write8 primitive I talked about before. So by overwriting the forward and the backward pointer of the large heap block, we write a pointer to the size field of the integer array. And we do that to effectively, basically by overwriting the size field with a pointer, you enlarge the size by a really large factor. And a quick refresher on how arrays are stored in memory. So basically you have three length fields. You get the number of allocated bytes, you get the actual array length, which is the number of currently stored elements in the array. And finally, you got the reserved length. And during the write8 primitive, or with the size corruption we just overwrite the reserved length, which allows us to use this array to actually write out of bounds. However, if you want to read memory after the array, you actually have to modify a second length, namely the array length. And instead of corrupting two length fields, what you can do is you first corrupt the reserved length, and then you write at a really high, at a really large index, which is larger than the original size. And that will effectively adjust the array length accordingly. So after doing that, you have the ability to read and write memory after the actual integer array. So the second step is actually to do exactly this. So we are using the first integer array where we overwrote the size field, and we write to a really high index. And now you see why we chose to use this memory layout, because we are writing to the first element of the second integer array. And we are doing that in order to not corrupt any unrelated memory, to not cause any crashes. And also it gives us the ability to see if everything worked, basically. Because you can easily check the element of the second array, and if you successfully modified that element, you can be sure that from that point on, we are able to read and write to all this memory between these two integer arrays. So the last step is basically, now that we are able to read and write between these two integer arrays, we want to modify a typed array. So first we leak all the typed array pointers from the array of typed arrays. And for every pointer, we are basically checking if the reference typed array resides between these two integer arrays. And if it does, then we are able to access it, right? So we just overwrite the size field and the raw data pointer of the typed array. And then we have a typed array which allows us to to read and write arbitrary addresses, basically. For 64-bit processes, there's still some issues you're running into, mainly due to the way or that you can't write really huge size fields, but you can easily work around that fact, and it's all described in the white paper if you're interested. So now we got the ability to read and write arbitrary memory. So this is quite powerful. And we can also leak arbitrary JavaScript objects. So if you take a look at the slide again, what you can do is you can store arbitrary JavaScript objects in the array of typed arrays, and then you just use the corrupted integer array here to leak one of these pointers, and you immediately get the address. So what do we do with it? So the most obvious thing to do is, okay, let's get the address of a JavaScript object, and we just overwrite the vtable pointer and get code execution. However, on the latest version of Windows, you have control flow guard. So it's not that easy. I mean, you would need to find a bypass, a CFG bypass, and it might be quite some effort. And also, using shellcode and ROP gadgets and all that stuff might give you some more work later on when we want to bypass Emmet. So in the end, we decided to go another route, and namely, we were looking into God mode. So God mode is a known technique. It was publicly presented by Yang Yu and Yuki Chen in 2014 already, and it's basically an attack against IE's script interpreter engine. So in the past, what you could do is in the script interpreter engine object, there's a single flag called a safety option flag. And in the past, what you could do is you could just overwrite this single byte with a single null byte, and that would basically give you the ability to instantiate arbitrary unsafe ActiveX controls. And effectively, you can then execute any system command without using shellcode at all. So inside the code, there are two functions which are responsible for deciding if this is possible without any prompts. which is script engine can create object and script engine can object run. So once this was published, Microsoft decided to do something about it and tried to make it a little bit harder. And they introduced a 20-byte hash code. So this is basically a way of trying to prevent you from just overwriting a single byte. Some more details about this are nicely documented in a blog post by Fortinet. And actually, there was a bypass for that as well. So in Yuki Chen's xplib2, which is quite awesome, he implemented a bypass. So instead of overwriting the safety option flag, what he did is he replaced the complete reference to the security manager object. And so he's basically building the security manager object, a complete new security manager object in memory, and overwriting the reference to it in the script engine object. And then what he does is in the vtable of this fake object, he's basically replacing two function pointers with dynamically generated ROP gadgets, as you can see on the bottom here. So this worked nicely. However, once CFG was introduced, the way it was implemented no longer worked. I mean, you could probably adjust the technique and use some specific CFG or some specific ROP gadgets instead. But instead, we found a much easier way of doing it. So I started analyzing the code, and in particular, I was interested in if it would be possible to still use the God mode technique. So I was looking for the code mentioned in the previous Fortinet article, and I was looking for the code which basically does this hash code verification and calculation, all that stuff. And I was looking, and I really couldn't find the code. So I was thinking, okay, maybe I'm just too stupid to see it. So in the end, what I did is I just overwrote the safety option flag in order to see what would happen. And it turns out it still worked. So I was a little bit confused. So it looks like you can still write a single null byte and get code execution. It turns out the protection just disappeared. And later on, I found out the protection actually just disappeared on Windows 10, so where I did my analysis, obviously. So on Windows 8.1, for example, the protection mechanism was still there. So interestingly, this year at CanSec West, I was talking to someone from Microsoft, and they told me that this hashing protection thingy, it disappeared due to an internal compiler change, which I found really interesting. So in the end, we still had on Windows 10 the ability to write a single null byte in memory and get the ability to execute system commands. So now this gave us the ability to get code execution. However, as I said, we were targeting the enhanced protected mode sandbox since this was a requirement for Pwn to Own. So let's see how we can maybe escape that. Again, we did some research on what people used in the past to escape the IE sandbox. And there's a known and public technique which was used in the past by people to escape the protected mode sandbox, so the less restricted version of the sandbox. So it's based on the concept of zones. So zones allow you to basically define security settings for different groups of sites. And it turns out that the protected mode and also EPM is not enabled if a page is considered to be part of the local intranet zone or the trusted site zone. So every time your page is considered to be part of this zone, it's running or it's rendered outside of the sandbox. And it's rendered in a 32-bit process as well. So this was first documented in 2010 in a paper published by Verizon. And the basic idea is as follows. So once you get code execution in your first stage payload, you're basically starting a local web server which delivers your same exploit again, and then you just redirect IE to this web server. And since IE is redirected to localhost, it's automatically considered to be in the local intranet zone. So it's rendered outside of the sandbox. Here, so you just trigger the exploit again, and then you get code execution outside of the sandbox. And this was, as I said, already exploited several times in the past. So the Verizon guys did it. ZDI exploited the same vulnerability during the Pwn for Fun contest in 2014, for example. And the advisory published by ZDI is pretty interesting because you can see the response from Microsoft, where they state that it does not meet the bar for security servicing. And instead of fixing the bug, they did a recommendation. And their recommendation to mitigate this issue is to use EPM, so the Enhanced Protected Mode, which we are targeting. So why does EPM protect against that? So EPM is based on App Container, and App Container uses the concept of network isolation. And network isolation basically prevents a sandbox process from receiving new network connections, and it should also prevent you from, or the sandbox process, from sending or establishing new connections to the local machine. So we were thinking about that, and I mean, in general, we are not restricted to localhost. So all we want to do is we want to get a domain name which is considered to be part of the local internet zone. So and it doesn't have to be localhost. So we were trying to find out how IE actually decides if a site is part of the local internet zone. And there's one really simple rule, which is called the plain hostname rule, which basically says if the domain name of the URL doesn't contain any periods, it's automatically mapped into the local intranet zone. So it all comes down to, are we actually able to register in somehow a new domain name without any periods, which still points to an external IP address we control. And it turns out, yes, that's possible, and you can do that by doing local NetBIOS name spoofing. So again, this is not a new technique. It was, as far as I know, first implemented in Foxglove's hot potato exploit, and they used it for the purpose of local privilege escalation. So NetBIOS name service, or NBNS, is a UDP-based protocol, and it's used as a fallback mechanism if DNS fails. So you can just do a DNS lookup, and after a few seconds, if the hostname can't be resolved, you see all these UDP broadcast packets being sent. And if you do normal NetBIOS name spoofing, like in a penetration test, what you do is you just look for these request packets. You take the 16-bit transaction ID from the packet, and you fake a response. However, compared to the local scenario, we have a big difference, because in the local scenario, you don't see these outgoing UDP packets. So you can easily trigger these NBNS packets, but you won't see the outgoing packets. And that also means you don't see the transaction ID. But in order to send a valid response, you have to send the right transaction ID, obviously. But what you can do is you can just brute force it, right? So you trigger one of these NBNS request packets, and then you just flood the localhost with response packets with all different kinds of transaction IDs until you hit the right one. So this is just how one of these NBNS packets looks like. So if you listened carefully to until now what I said, you would think that this technique, local NBNS spoofing, shouldn't be possible from the EPM sandbox, right? Because there is this concept of network isolation, which should prevent you from sending packets to the local machine. However, it turns out there are exceptions. So it is actually possible to send UDP packets to localhost port 137. So in the end, we can just do local NBNS spoofing from within the App Container sandbox. And we did exactly that. So we tried to register a new domain name without any periods, which pointed to an arbitrary IP address, which we controlled. And we redirected IE to this new domain name, And then we exploited the same bug, which we exploited in the beginning, but this time in a 32-bit process. And that effectively gave us code execution outside of the sandbox. And again, we didn't use any memory corruption, any shellcode, any whatnot. So now, basically, we are already done, but we had still this requirement of bypassing Emmet. So let's see if we are actually affected by Emmet at all. So it turns out we are. So if you run the exploit under Emmet, you will see in the logs that the feature called attack surface reduction, or ASR, is actually preventing our exploit from running. And ASR is a feature which basically blacklists a number of modules which are considered to be dangerous, basically. So they're doing that by hooking the load library X function and then comparing the name of the loaded module against the blacklist. And in our case, they detect the use of the W script shell ActiveX control, which we are using to execute system commands. So let's see if there's a way of bypassing that. Again, we did some research on what people used in the past, and there's a quite nice article by FireEye about their latest Emmet bypass, which lists all the previous work on Emmet bypasses and ways to disable Emmet. So you can get a nice overview there. However, the difference to most of these techniques is actually that in the usual case, you already have the ability to execute ROP gadgets, or you have the ability to execute some small shellcode, which you can then use to disable Emmet. However, in our case, we don't have code execution yet. So the Emmet is actually preventing us from instantiating the ActiveX control, and only after we got the ActiveX control running, we get code execution. So we can't use any ROP gadgets, for example. However, we have our really powerful read-write primitive. So let's see if we can use that in order to disable Emmet. So if you take a look at the Emmet code, and in particular at the place where the ASR check is implemented, you're running into this small check here. So what it does, it basically reads a pointer from a known location in memory. It decodes the pointer using the decode pointer API. The pointer is pointing to a config structure on the heap. And at offset 28, there's another pointer pointing to a flag in memory. And if this flag is actually not set to 0, the ASR checks are performed. And similar checks can be found for other Emmet features as well. So the idea is, okay, we have a read-write primitive. So maybe we can just override this flag, right? That doesn't work because the people who wrote Emmet, they thought about this attack and they set the memory which is storing the flag read-only. Okay, so maybe we can override the enabled protection pointer pointing to the flag and point it to some other memory or to some fake flag. That's possible. However, you still have to find the address of the config struct on the heap. There's a reference, as I said, but the pointer to this structure is actually obfuscated using the encode pointer API function. So let's take a look at that. So if you take a look at the MSDN documentation for encode pointer, they give you some hints on what they actually do when they obfuscate pointers. So they say the pointer is obfuscated with a secret value, and this secret value is different for every process. So that means it's the same in our process for all the encode pointer calls. So the question is, can we maybe use our read primitive to leak the secret value somehow? Because if we manage to do that, we would be able to decode any obfuscated pointers in the process. So we took a look at the implementation of these encoded pointers, which can be found in RTL encode pointer and RTL decode pointer, respectively. And it turns out they're using a 32-bit secret value, which is also true for 64-bit processes, by the way. And they obtain that directly from the kernel. So they just do a call to ZW query information process, And once they got the secret, they're using it to do the calculation and then just throw it away. So it's not like it's stored at some static location where you could leak it, for example. So it doesn't seem to be possible to just read the secret value from memory. So let's take a look at the implementation of an obfuscated pointers. So this is some pseudocode for the 64-bit version of these functions. So what they do is they take the plain pointer, they XOR it with a secret value, and then they right shift the whole result a certain number of bits to the right. And the number of bits it's right shifted depends on the secret value. And this is most probably done in order to prevent simple XOR attacks, because if they wouldn't do it like this, you could just take an encoded pointer, the corresponding plain pointer, XOR them together, and you could basically calculate the secret value. However, there are only 3 possible right shift values in this case, which turns out to be easily brute forceable. So in the end, what we do is we obtain a pair of pointers. So we obtain a pair of known encoded and corresponding plain pointer from memory. And then we iterate over all the 3 possible right shift values. And we perform a partial decode pointer operation on the encoded pointer from our pair. And the result of that, we XOR it with a known corresponding plain pointer, which gives us a potential secret value. It doesn't have to be the right one, but it is a potential secret value. And in order to check if it's the right secret value, we just perform the encode operation. So we take the plain pointer, encode it with this potential secret value, and make sure or check if the result is actually the encoded pointer. This will eventually give you a secret value, and most of the time you will get the right secret value. However, there's a problem. So due to the way it's implemented, due to the right shift, due to the rolling right shift, there's a chance that you actually encoding the same pointer with different secret values could in theory result in the same encoded pointer, which isn't a problem in the normal implementation. But since we are doing it backwards, this can result in the scenario where we find a secret value which is the wrong one, which is bad because once we use the wrong secret value to decode a pointer, we get a wrong pointer and we would crash. So in order to bypass this, what we do is we just use a second pair. So we use another pair of plain encoded pointers, and we try the found secret against that pointer pair, and if it matches, then we know, okay, we can be pretty sure that this is the right secret value. So in order to find these pairs of encoded and plain pointers, you can basically take a look into any module which is loaded. We took a look in the emmet module itself, and it's quite easy to find these pairs. For example, on this slide you can see what they actually store the null pointer in encoded form at a static location in the data segment. So we know the plain pointer, it's null. The encoded pointer can be read from that location in memory, and finding more pointers is not that hard. So in the white paper we have another example on how to find another pair in emmet64 DLL. And in general, you just search for the use of encode pointer calls. So now that we are able to leak the secret value, we are able to basically deobfuscate all the pointers in memory. So what we do is we first leak the emmet64 base address, which is easy because emmet is hooking many functions, such as anti-protect virtual memory, which is one of them. And so you just read the first few bytes of that function and then basically follow pointers until you find the base address. And once we found that, we leak the obfuscated pointer from the data segment. We decode it using the extracted secret value, and that way we find the address of the config struct on the heap. And once we found that, we use our write primitive to overwrite the enable protection pointer, and we just point it to some memory which happens to contain null bytes. So in the end, this is enough to bypass emmet, or the ASR check in this case. And as I said before, this kind of technique can probably also be used for all the other emmet checks as well. So now we got code execution outside of the sandbox, and we successfully disabled emmet as well. So my conclusion, first of all, the current patch status. So the typed array neutering vulnerability was already fixed in MS16063. And interestingly, the same bug was already fixed in the Chakra core engine since its publication on GitHub. So it looks like this was some kind of overlooked security fix backport, maybe. The EPM sandbox escape using local NetBIOS name spoofing was fixed in MS16077. And interestingly, the same bug was found by Yang Yu and was used for his bad tunnel research, which he presented this year at Black Hat. The God mode single null byte technique was fixed in MS16051. And interestingly, they, instead of reintroducing this hashing mechanism, what they do now is they use the query protected policy API function, which is used for exactly this purpose, so trying to prevent people from modifying certain data, which is considered to be important. And last but not least, the emmet bypass is not fixed, and what I heard is there are no plans to address it in the future. So it looks like if you got the ability to read and write memory, which I must say is a really powerful primitive you first have to get, but if you got that, then you can easily bypass emmet. So my conclusion is, of course, modern exploit mitigations increase the effort quite a lot in order to build exploits. However, with the right vulnerability at hand, it's still possible to bypass many of these mitigations. And I mean, many people think that once CFG is really really hardened and there are no easy ways of bypassing CFG, then exploitation will be over or whatever. Just keep in mind that it's not really necessary to take over the control flow. So sometimes it's also possible to just modify some data, and that way basically get all what you want. Just people did it in the past because it's of course much easier to redirect to your own shellcode and implement what you want to do, but it's not necessarily required. And in general, about these kind of data-only attacks where you get the ability to read and write arbitrary memory, you can use them to bypass many mitigations. And in general, what you can target basically any functionality. I mean, there are functionalities which are obvious, like instantiating unsafe ActiveX controls. That's a really dangerous thing to have in your code, obviously. Or if you take a look at other browsers, like for example Firefox, there you have the ability to execute JavaScript code in Chrome context, which gives you all the access to the operating system, basically. But there are other functionalities which don't seem that obvious, but they can still be targeted. And in general, so that's just my personal opinion, but I think that once all these CFI solutions mature and all the easy bypasses are gone, if that happens, I don't know, then I think then more and more people will actually make use of these data-only attacks, because they are really hard to defend against. So here are some of the referenced works. And yeah, that's it. Thank you very much.